At this time, it is my absolute pleasure to introduce our next two speakers. We'll have Donna McDonald-McGinn and Beta Nowakowska. Donna is the director of the 22q Center and the chief of the Genetic Counseling Section at the Children's Hospital of Philadelphia. As the chair of the 22q11.2 Society and a founding board member of the International 22q11.2 Foundation, she leads global initiatives focusing on chromosome 22q11, the copy number variants. With over 350 publications, including a textbook, she specializes in understanding outcomes in patients with chromosome 22q11.2 deletions and variants, particularly TANGO2 Deficiency Disorder. Donna currently serves as a member of the TANGO2 Research Foundation Scientific Advisory Board. Donna works directly with Beta Nowakowska, a researcher in the Department of Medical Genetics at the Institute of Mother and Child in Warsaw, Poland. Beta has also served as a trustee of the 22q11.2 Society and 2024 program chair. She's published research exploring pre- and postnatal diagnosis of TANGO2 deficiency disorder and genotype-phenotype correlations with TDD and 22q11 deletion syndrome. Her research aims to uncover how genetic links could offer key insights into the biology of TANGO2, bringing us closer to better understanding earlier diagnosis and smarter treatment strategies. She will be joining us virtually, but first, please join me in welcoming Donna McDonald-McGinn to the stage.
Thanks so much for the lovely introduction, and it's really a pleasure to be here. I am certainly not an expert in TANGO2. You all are experts in TANGO2, but I can talk to you about chromosome 22q11.2 deletion syndrome and the association with TANGO2 deficiency disorder. As you'll see, the real expert is Beta Nowakowska, who is actually the chair of human genetics at the Institute of Mother and Child in Warsaw. So, for those of you who don't know much about the chromosome 22q11.2 deletion, it results in loss of about 50 genes, leading to a multi-system disorder with significant morbidity and some mortality. And 22q11.2 deletion syndrome is common. We talk about the fact that TANGO2 is a rare condition. 22q still counts as rare because the prevalence in live births is less than 1 in 2,000, but it's pretty darn close. It's been found in 1 in 1,000 pregnancies, 1 in 1,500 miscarriages, and it's the second most common chromosomal abnormality after Down syndrome. It's the most common cause of syndromic palatal abnormalities and schizophrenia, and the second most common cause of congenital heart disease and developmental delay after Down syndrome. And 22q11.2 deletion syndrome is not associated with advanced maternal age, so affected offspring are equally likely to be born to young mothers as to those with advanced maternal age. So based on a prevalence of about 1 in 2,000, there should be about 167,000 affected Americans, including 37,000 children and adolescents, which begs the question, where are they? Because at CHOP we have the largest clinic in the world dedicated to caring for patients with chromosome 22q differences, and we only follow about 2,300 patients. So perhaps these individuals are still waiting to be diagnosed. Now, 22q11.2 deletion syndrome is also associated with additional birth defects, later onset medical conditions, developmental delay, cognitive deficits, behavioral health issues, and as I mentioned, psychiatric illness, making it an important window into understanding both common and rare associated features and providing abundant opportunities for gene discovery, novel therapeutics, and personalized healthcare, which is something we're all looking for. So 22q truly is a tiny piece leading to a big picture. But 22q11.2 deletion syndrome is variable in all areas, including in adults identified only following the birth of a child with congenital heart disease, such as in the father on the left and the mother on the right. And this variability extends across the lifespan between patients and even within families. So how do we explain such variability, which we see again across the lifespan? Well, our data suggests that deletion size impacts variability. Although most patients, 85%, have a standard A to D deletion. Let's see if I can figure out how to use the pointer. Is it here? Well, I think it's not working. Anyway, is it working? There it is. So most patients have a deletion that goes from this low copy repeat, which are just duplicated sequences that don't cause a problem in and of themselves, to this over here, so A to D. But a subset of patients have nested deletions within the A to D region, so A to B, A to C, B to D, and C to D. And this is important because those patients who have B to D and C to D deletions would be missed by the most common lab test used to detect the deletion, which is a FISH study, which is over here. We developed those FISH probes at CHOP in the early 90s, but we haven't used them for years for this reason. And so when we examine things like prevalence of associated features by deletion size, we see, for example, that congenital heart disease is statistically significantly less common and less severe in patients with B to D and C to D deletions, even though there's a cardiac developmental gene within that region known as crackle. We also see that hypocalcemia is only observed in 2% of patients with B to D deletions and no patients with C to D deletions. And the same for palatal abnormalities. We found none in those with C to D deletions. So deletion size matters. In addition, many nested deletions are familial compared with the A to D deletions. So when we had both parents available for testing, we found that 14% of A to D deletions are familial as compared to 22% of A to B, 17% of A to C, but a whopping 71% of B to D and 67% of C to D. So nested deletions impact variability, and this information is key in providing personalized health care, including, of course, recurrence risk counseling. This may also help to explain the overall under-ascertainment of chromosome 22q differences if people are still using FISH studies. But what else may explain the variability that we see? It can't all be deletion size if 85% have an A to D deletion. Well, some features are affected by genome-wide modifiers, such as for congenital heart disease, as shown by Bernice Morrow and our International Brain Behavior Consortium, looking at polygenic risk scores and the prevalence of psychiatric illness or schizophrenia. And other features are explained by dual diagnoses unrelated to 22q because 22q is common. So we have a subset of patients with the 22q11.2 deletion and a completely different diagnosis on another chromosome. So we have a child with severe combined immunodeficiency due to autosomal recessive Artemis deficiency. We have a child with 22q and cystic fibrosis, et cetera, again, because it's common. Now, still other features may be due to dual diagnoses related to the chromosome 22q11.2 deletion in patients with a deletion on one chromosome 22 plus a variant on the remaining non-deleted chromosome 22. So, for example, in patients with craniosynostosis, significant short stature, anal anomalies, including imperforate anus, and skeletal differences, mostly thumb and radial anomalies. And this is due to variants in CDC45 on the non-deleted chromosome 22, unmasking an autosomal recessive condition known as CGS or Meyer-Gorlin syndrome. Now, there are multiple additional examples of what I call rare squared, and that involves genes within the 22q11.2 deletion, including GP1B beta, SNAP29, LZTR1, SCARF1, PROD-H, and of course, why we're here, TANGO2. And these result in multiple conditions, including Bernard-Soulier, which is a platelet disorder, Sednick syndrome, which is associated with polymicrogyria and keratoderma, autosomal recessive Noonan syndrome, Vanden and DeGupta, which is multiple dislocations of the joints, and proline dehydrogenase deficiency, and all with their own specific additional problems. But the most significant example is TANGO2 Deficiency Disorder, as you know, and when we wrote this paper in 2015, we didn't know about TANGO2 because Seema's paper came out in 2016. And TANGO2 is located between A to B, as is CDC45, and again, we really didn't know about the importance. And we only became aware of the devastating impact of changes in TANGO2 on the non-deleted chromosome 22 when we met Robert. I've talked about Robert before, and Debbie is here. And Robert was diagnosed with the 22q deletion at 10 months of age, and he had very typical features of the deletion. But he had additional atypical problems, which is why he came from North Carolina to see us in Philadelphia. He had torticollis, he had episodic ataxia versus dystonia, he had difficulty waking following anesthesia, staring spells versus seizures with a normal EEG, and he had really significant weakness and extreme fatigue. And sadly, in 2015, again before Seema's paper, Robert passed following a brief illness. And it took from 2015 to 2018 to make a diagnosis in hindsight. And we learned about TANGO2 during this time, and we sent clinical studies off to a well-known national laboratory, and they told us it was normal, even though we said, please look at TANGO2. But we didn't give up, and Bieta ultimately identified an exon 3 to 9 deletion in TANGO2 on the non-deleted chromosome 22 allele. Now, no question, having Robert's diagnosis in its entirety was enormously helpful for Robert's family as well as for his care team, because, of course, we were devastated by his loss, and we only wish we had known while he was with us. So together with Dr. Nowakowska in Warsaw, we vowed to elucidate the importance of 22q and TANGO2. So I'm going to pass it over to Bieta, and she's going to tell you about the aims of our study, which you'll see were supported by the TANGO2 Foundation, and then it's going to come back to me to talk about the phenotypes associated with what we found. Bieta.
Good morning. Thank you so much, Donna. I hope you can hear me. Can you hear me? Okay, thanks. So thank you so much for the invitation. I'm very sorry I can be only online, but I'm in Poland and I couldn't come. But yes, today I would like to show you what we have done in the project which we got from the TANGO2 Foundation. And if I can ask you to change the slides because I don't have the... one more. Okay, so the aim of the study was to mine existing databases which we had access to. So one was the database of the International 22q Brain and Behavior Consortium, and also the database which we have created with Philadelphia with Donna for the last few years, which included the patients from Philadelphia and Poland. And for these patients, we also in most also the RNA-seq and genome data. So we have collected in total more than 1,700 samples. 1,300 were from the IBBC cohort, almost 100 from Poland, and almost 300 from Philadelphia. And the aim of this project was to look at the databases and look for the rare variants in TANGO2 to identify patients which may not be identified as those which have the 22q deletion and TANGO pathogenic variants. We also hope that identification of the new variants, where we only need one variant to be causal, we can identify new pathogenic variants which we can be associated with the TANGO2 disease later for the patients which don't have the 22q deletion. Okay, so we have looked for the variants which were loss of function, missense, and some deletions which are not the common deletions, but different deletions without the TANGO2 gene. We have looked for the rare variants which are not common in the open databases, and we have identified 18 patients within IBBC cohort. And some of them we have looked at in the GNOMAD database. GNOMAD database basically include only patients which are not severely affected. So we looked at the variants which are very rare in the GNOMAD and which do not have homozygote variants in GNOMAD as the variant probably would be pathogenic itself. So we have identified 13 patients with the same variant, which we have excluded, and also one patient, which we also on the beginning excluded because it was also described in GNOMAD at the homozygous state. We have focused on the 4 patients which were identified as a very rare in the general population. And all of these variants were missense. We also looked at the cohort from Philadelphia and Poland, and we have identified 3 patients with the 3 to 9 deletions, which is the recurrent, the most common variant seen in the TANGO2. We have identified 2 missense variants which were not known as a pathogenic before, but we know that the patients, they have a full spectrum of TANGO2 syndrome. We also have identified 1 atypical deletion in exon 9, which was not described before. And this exon 9 deletion was very of particular interest because it was very atypical, and also we had to look back at the phenotype of the patients to really look if it's causal or not. So on the top here on the left side you have 3 plots of genomes. So on the top you have shown small deletion of exon 9. The exons are on the bottom part of the picture, and like the thick blue line indicates the exon 9. And when you look at the top of the picture, there is like small gap which is within the exon 9. And below you have 2 patients with the deletion of exons 3 to 9. So you can compare the sizes of the deletion. On the right side, you have also we have also shown the expression, because one of the patients with the deletion of this typical deletion 3-9 exons we identified by the expression. So in the middle you have in the very like on this blue bars, you can see that one of the blue bars is very low. It means that there is a deletion, the patient of the deletion with also 3 to 9 exons. So when we looked at closely at the exon 9 deletion, you can see that there is something going on within the exon which makes the expression different when it's compared with the typical patients without the deletion in TANGO2. Can you go further? So on the top again you have the patient's expression with the this 9 exon deletion. Below 2 examples of patients with deletion of 22q but without any variants in TANGO2. And you can see here in this patient on the top, you can see that there is this protein, this RNA is longer than it should be. So we don't don't really know yet how much it affects the phenotype of the patient, but definitely the expression is different than it should be.
Okay, so if we then move on to the phenotypes, the 4 patients who were identified with rare pathogenic variants from the IBBC sites, they came from 3 sites. So one site had 2 patients, and then there were 2 additional sites. All are outside of the U.S., and unfortunately, 2 of those 3 sites have told us that they have lost contact with the patients and that they will have no further information for us. But we went into the IBBC databases and we found that all of those patients had an intellectual disability, which is generally different from our 22q cohort, where our mean full-scale IQ is 76, and usually we have a higher verbal than performance IQ. So we think that that's indicative that there's an issue. The remaining site has contacted the patient, and they're bringing that patient back, who's an adult, for additional evaluation, and we'll see what they find from a neurologic perspective. When we look at the USA Poland cohort, which was an N of 6, we then went and examined the phenotypic features in more detail, including morbidity and mortality. And so when we look at mortality, the index patient was Robert, and he, as you know, passed at age 5 years. The other 5 are living at ages 24, 19, 18, 9, and 4. And then when we looked at morbidity, again, Robert's across the top, and I talked a little bit about what his features were, including that he had significant speech and language deficits, and he was nonverbal when he passed at age 5. But if we look at the others, and by the way, Robert had hypothyroidism, you'll see patient 2 from my group had hypothyroidism. He has epilepsy, poor balance, tight heel cords, severe dysarthria, severe intellectual disability, and he recently had a psychotic break, which we are attributing to the 22q deletion, not to the TANGO2, although you'll tell me if you've seen psychosis in your patients. I haven't seen it reported. Patient 3 is under the CHOP umbrella because they were referred to us from Phoenix, but these are actually Terry Greby's patients, and she called because she said, I think this patient has TANGO2. The patient had a right bundle branch block, had hypothyroidism, severe epileptic encephalopathy with spastic quadriparesis, severe hypertonia with spasticity, joint contractures, again, intellectual disability, stroke-like event with seizures following a strep infection, and loss of verbal skills. And patient 4 is from our group. Elevated triglycerides, tight heel cords, toe walking, bilateral knee and ankle contractures, and this is the patient that has the atypical deletion in exon 9. So found this patient at 19 through this work with Beata, and went back to her and sent her to neurology, and they're doing an additional workup. It certainly feels like she has some features consistent. Patient 5 is from Beata's group in Warsaw with hypothyroidism, a WISE-based spastic gait, and this is the youngest patient, and global developmental delay ID, and is nonverbal at age 9. And then patient 6 also came to us from Terry Grebe in Phoenix, and the patient has poor balance and coordination, was admitted with quote-unquote TANGO2 spells, dystonia, dysarthria, drooling, lethargy, a head and body tilt, developmental delay, and ID. So in summary, we've identified 10 patients from 1,700 with variants in TANGO2 for the combined IBBC and CHOP Warsaw cohorts, resulting in an overall prevalence of 1 in 170 patients with a 22q11.2 deletion. All were rare variants not reported in NOMAD, and as you heard, deep phenotyping was only available really for the USA Poland subcohort. Findings were consistent with TDD features, including 1 death, 4 of 6 with hypothyroidism. I just saw the thyroid poster out there, and this is a bit higher than what you all have seen at 67%. If we count in the IBBC patients, 8 out of 10 had an intellectual disability. And then there were TDD-related neurologic findings in all patients to varying degrees, including dystonia, ataxia, balance issues, tight heel cords, hypertonia, spasticity, contractures, and dysarthria. So in terms of future directions, given the frequency of rare pathogenic variants in TANGO2 in individuals with 22q, and the fact that TDD is treatable, we feel like early identification of both conditions is critical. So moving forward, we're hoping to design a newborn screening pilot study as soon as possible to identify both conditions, and we're hoping to do this with Beata at the Institute of Mother and Child in Warsaw, because I mentioned she's the chair of genetics there, and they are the hub for all newborn screening in Poland. Every newborn screening study, every blood spot comes to Beata's group in Warsaw. So we feel like this is an opportunity to really get our handle on it, to see what we see in the general population, and then to make it into law in Poland. And once that happens, then everybody else will follow. And we feel like it's scalable. So I'll stop there and say we'd like to thank our collaborators around the globe, because it always takes a village to care for a patient with 22q, especially the members of the IBBC, and support from 22q11 Polska, and of course for the families with TANGO2 Deficiency Disorder. And always want to thank the patients and families for everything that they've taught us, because like Robert, it always begins with the patient. And special thanks to the TANGO2 Research Foundation for supporting this important work, because without the funding, none of this would have been possible. We would have never done it. So thanks so much. And maybe we can bring Beata back for Q&A. There she is.
Questions?
That was great. So just to highlight, I think we have an ascertainment bias, and we've talked about this, Donna, but there's a bell curve of severity, and we probably catch the people in the middle, and we miss the really mildly affected, and we probably miss the kids that are too sick and pass away before we get a diagnosis. So in addition to identifying new patients, for the sake of identifying these patients, we're learning about TANGO2 and the spectrum of phenotypes that might present. And really, this is the this approach is the only way you get there, really. I had a question about...
Can I just say one thing about that? I was just in Poland, and we were back and forthing about the one patient in Nomad who is unaffected. And the question is, how unaffected is that patient if it's one patient, and should we really be counting them? Because we don't know about the mild end. Completely agree, Sam.
And my question was about, I missed the middle slide, I think, with your variants. How many of the 10 were missense variants and novel missense variants? And have you looked at kind of where those occur in the protein?
Yeah.
All of them are missense variants.
Not the deletion.
From the IBBC cohort, yeah.
Related specifically to the genes, but a quick question. I saw there was a common thread with either kyphosis or scoliosis on those individuals. And do you think that's a result of just low tone as they're developing and they're growing up, or is that possibly a subset of findings?
We see scoliosis in 50% of children with 22q, and 25% go on to need bracing or growing rod placement. So I think it's hard to say. We also see vertebral anomalies. But certainly, if you have low tone, you're at greater risk for developing scoliosis. So it could be a combination.
Hi, Beata. This is great work, and I'm sure that a lot of people share the enthusiasm we have about the newborn screening that you will start. Thank you for doing that, because this is our priority, and we would love to see what you find there. Question for Donna. So you see hypothyroidism in 22q, you see seizures, but is there something different about combination or with the gait abnormality, something that you could say that a child walking in a 22q, you should think about these conditions? And it's for clinicians seeing these patients in the clinic on a regular basis.
Well, I think, first off, our experience is very small. The numbers are small. But there's no question when we saw Robert, we said this is atypical. You know, we don't see patients with this wide base gait. We don't see intermittent dystonia or ataxia. I think there was a debate. Sarah Hopkins, the neurologist, said it was definitely dystonia. Others said it was ataxia. I think that we see a fair number of kids with tight heel cords, and, you know, we also have a subset with tethered cord, so we're constantly sending them to neurology to think about tethered cord, and then when they don't have it, could it be this? We see a lot of hammer toes. We see a lot of progressive hallux valgus. I mean, I think we don't know, but we are now prospectively sending studies in every single patient with a deletion. The problem is the lab that's now doing it for us missed the patient with the deletion in exon 9. And so we're waiting to have a meeting with them to say, how did you miss this? Because Beata's feeling is they shouldn't have missed it. And we know that other labs have missed the regular 3 to 9 deletions. So to be honest, I have no confidence in the clinical labs at all. And I wish I could do all my tests with Beata in Poland. She's CLIA certified, whatever the certification is called in Poland. It's just a nightmare to send it out of the US and get it done there. Unlike the old days when we send NF1 testing to Germany. So I don't know what the answer is. And we have, you know, our big 22q meeting is in 2 weeks. There are multiple presentations about other sites that are now sending studies on the other allele just for this reason, because they heard Sam and Christina speak at our big meeting in 2024. But I don't know what the results are from those groups either, if they've had a clinical lab identify a variant. And I know Christina's had the same issue in patients being missed. Beata, you want to add to any of that?
No, I think you have said all. I think the clinical picture is the most important right now to really identify what's important, what's not.